and views.
It is really a pleasure to join this FFP talk today. And I would give you an overview on some of the research about multimedia forensic and security that I've been working on in collaboration with a number of my students and my collaborators, and actually one of them is the alumni of the applied math department here, who is applied mathematician as well as electrical engineer, which I've been here is a faculty now at Winlab Rutgers. So in recent years, we have seen a lot of advances in multimedia technologies. The MP3 players, digital cameras, and all this has really changed the way we live and work. And increasingly, we have seen in order for all this multimedia technology to reach their full potential, we need to make sure we have the content being used by authorized users and only for authorized purposes. And when security and policies got compromised, we need to have some technology to help us reconstruct what has happened, who is the guilty person, and what has happened when, where, and how can we improve our system and also make those guilty person accountable. So these are the questions about the image origin, integrity, who will distribute to, and who leak information along the entire chain of how the images, the video, and the audio go through from the point we capture, we archive, the storing, and the distribution. So increasingly, this is an active research area in signal processing and coupled with a number of areas bringing in the machine learning, communication, detection, and cryptography. To do security forensics, we need to gather traces of evidence. And just like in traditional criminal science, the film and fingerprint play a very important role. And here, we're going to explore the digital fingerprint in the content. And this term is really well liked by many colleagues in our field. They work on technology called their technology fingerprint, but they mean slightly different things. And here we summarize three major types of digital fingerprint. And I use, just to remind you of our weather here, I use eyes to summarize it. So let's go backward. The E type is the embedded fingerprint. Here the idea is we have a picture, we embed something invisible to our eyes, but it's a traceable, it's a unique signal or ID code that will be identifying to whom we distribute to. So if President Obama have a satellite picture shared with his cabinet, someone leaked to Washington Post, he will be able to know who was the source of the leak. And then on the other side of the spectrum, we have the intrinsic type, because if we do not have any of this proactive technology, beforehand embed this trace of evidence, what can we do? We just have the picture. Can we, by analyzing the picture, those pixels, those completions, to analyze their relationship to say, how this picture was generated? Is it by a camera or by a scanner or maybe by computer graphics? Just to make it very similar to a real world, but it's actually not a real world scene. And whether there's any places has been tampered, the license plate may be doctored to a different number. So can we, by analyzing just the image characteristics, the relations among those numbers, to figure out the origin, the integrity, and the provenance? So this is an area that emerging is to explore the inherent traces which we call as an intrinsic fingerprint of this information processing chain. And since many of the things today, you really can't go away without Google. And with that linkage, bring us to the content fingerprint. Right now, if you upload a video you want to share with your friends or make your website really really popular, you could upload a copyrighted material, but Google and YouTube would have the technology to match this against a database. And otherwise, they will be sued by the content industry for copyright infringement, for facilitating copyright infringement. You have a potentially a large number of videos, copyrighted content. How to do this efficiently is by deriving something from the content, from the video, from the picture itself, and making it a very compact stream so that we can match against with a very high scalability and performance. So these three types, I will give you an overview and emphasizing the embedded and intrinsic type. If you have little time or offline, I would be happy to talk to you about some of the recent techniques, recent research we've done on the content. mentioned, the idea here for the embedded fingerprint is to put in a unique signal, a unique ID, which will help us pinpoint the individual user. If someone needs information, we would have some surveillance mechanism, for example, posted online, we will see whose ID is there and match it against our database and identify who was the source of the info. And here, we are facing a number of conflicting requirements. We want it to be invisible, does not interfere with the visual quality, visual content. We want it to be robust because our bad guy who want to leak information has all the incentive to try to remove it before they do the leak. We also want to have the tracing accuracy. We do not want innocent user to be falsely accused. And here, we are also facing not just the individual users who may have gone through our math department or our engineering department, know what's the best filtering to do to try to remove those fingerprints, but they can also collaborate. And in fact, this embedding side alone may bring you the relations to the digital watermarking, but digital watermarking typically are dealing with an individual adversary who could do compression or filtering. But now, we have the same picture, the same satellite image distributed to multiple users, and each version you putting in a slightly different fingerprint. If your adversary has got hold of multiple such versions, they could compare and they would figure out where the difference is and then try to generate a new version. Through such collaboration or collusion attack, they could be successfully removed if your fingerprint is not designed properly. So our research goal is trying to design reliable fingerprint that can be fighting against both individual and collaboration. And here is one of the illustrating example. We have a terrain map where full of curves, and we distribute multiple copies. Each copy uniquely imprint a particular fingerprint signals. And if, for example, we distribute this to our troops and their allies, and if some of them have their own agenda, they want to leak to our enemy, but they know you have the fingerprint traces, so that's a deterrent power. What they want to do is they collaborate. They try to figure out what are the differences and they try to averaging out the differences. And through this attacked version, if we use our collusion-resistant fingerprint detection system, we match against the database. The horizontal axis is the index of about 1,000 users' fingerprint. We see 5 peaks in our detection, and those are identifying the 5 contributing users' fingerprint. And similarly, they do different collaboration. If they piece together some of their elements and then merging together into one version and then leak, we will see 2 unique peaks and identifying treating back with these 2 users. And if those attackers print out their maps and then distribute, what we have developed is a high-resolution alignment algorithm, which will scan your picture and then back and then do the alignment and then run through our collusion-resistant fingerprint detection, and we'll still be able to see very good peaks, except because this printing and scanning is really a serious degradation, distortion peaks is lower compared with the digital copy. And when we design the fingerprint, we need to tailor to, depending on what type of content we are looking at. For grayscale and color pictures, we can look at those pixels or in the transform domain, such as the wavelength or ECT domain. For other data sets, such as this terrain map, what we did was looking at a good feature where we can do some local manipulation, making them so small that it's within, that our eyes cannot really see them, but we can use a detector to aggregate those little changes that all throughout the picture to make a reliable decision. So what we did there was to do some parametric curve modeling, identify a set of features as the location of the control point, where we manually perturb those locations and imprint our fingerprint information. It can also be applied to other types of data. So depending on the data we play with, we need to really tailor those are good features where we can do some minor local perturbation and collectively will carry our fingerprint. And then to uniquely identify individual users, we need to make sure our fingerprint has desirable properties. A simple way is to make those perturbations as causing orthogonal or uncorrelated factors so that we can uniquely identify them through a correlation detector. But strict orthogonality also limits the number of users where we can assign the fingerprint to. So there are some strategic correlation designs where we can go through the hierarchical build-up or through designing some good codes and then try to have good ways to embed it. Decoding ways, we separately design the code and then we figure out using watermarking, for example, to reliably embed it into the picture would work well if you only face a single user as the adversary. But when you have multiple users have this collusion, this separate strategies actually would have very limited collusion resistance. So our research actually have shown if you can jointly designing the coding and embedding layers, we can have a better scalability and collusion resistance. And here is why. By choosing your embedding strategies properly, for example, if we, for each of the bits, we will have a binary representation, and then when we do the embedding, we will use a spreading pattern. So this can be uncorrelated pattern, and each will be modulating based on the bits values we want to put in. If those spreading patterns are orthogonal but spreading out, so their support is across the entire picture, then what a attacker can see is the aggregated effect, but they cannot manipulate individual bits, and that putting on the effect of their collusions on code layers much less stringent. And then we can design code to have a good strategy with good properties. And here is an example, and in collaboration with my colleagues with different expertise, including Professor Travi that I mentioned, who have brought in this code expertise. So here, by doing that overlapping embedding, we limit the attacker strategy so that when we assign this code, where the binary is mapped to an antipodal, this is for user 1 and user 4, when they come together to collaborate, their effect is basically like the averaging on their code level. The attacker cannot manipulate individual bits. All they can do is the global effect. And then we can have our code designed to have a good combinatorial property. For example, only user 1 and user 4's code word can give us a shared once that is sustained after collusion, and all other places have a non-sustained bits. And by looking at this, we have properties only user 1 and user 4's code word can have this collusion pattern. And that, by looking at that, we will be traced back with a high probability to user 1 and user 4. Now, in other situations, if you are playing with video, it's not possible, feasible to really spread one bit to the entire 2-hour video reliably and efficiently. So when we are looking at those spreading patterns that have finite support, what we did was to couple it with some permutation properties, so that again, the idea is to limit what an attacker can do by jointly considering the coding and embedding properties. And here, if we're using the code level alone, for example, using a good error cracking codes, the code level can only sustain 5 collusions. Out of that, so this is the horizontal axis is the number of colluders. The vertical axis is the probability for detecting, for catching at least one of them. And you can see after about 6 colluders, our detection performance drops sharply. But using the same code, if we couple with a good permuted embedding, we can boost the collusion resistance by 4 times. And this would be helping us to use it as a building block to assign fingerprint to a large number of users. We have designed a prototype system that can accommodate hundreds of millions of users and have also very good collusion resistance. So far what we have seen is a proactive technology where we design fingerprint beforehand and And then later on, we utilize them as our traces of evidence to catch who was the source of the image. And you may ask, many of today's systems may not even yet have those fingerprint placed in. And when we receive a picture, can we figure out what is the origin, where did it come from? Is it trustworthy? So these questions about integrity, origin, and provenance really arise a lot from law enforcement, from intelligence operations, as well as journalism. When news agencies receiving a picture, they want to know whether this has been doctored. So what we have done is actually by looking into those data, just the pictures, we actually can tell a lot about their history. This is because using this imaging as an example, this imaging device has many components. The output we obtain is really a result of having gone through all these major processing components. And such processing chain can be applied to devices as well as other image processing or communication systems. Now, our question then is, can we, by analyze this, to infer what kind of techniques and what kind of algorithms inside the sum of these components? And what are the parameters can we estimate, like solely from this output image? And actually the answer is yes, in many cases, because this image is a result having gone through all this processing chain. And they may imprint, each of the components may imprint some invisible, but can be analyzable and detectable traces. And if we can do that, we could utilize our component forensic results to serve as a good trace of evidence to help us answer many of the questions that I raised earlier. Let me be a little more specific. Doing the component forensic is really depending on what you have. If you can break apart, you can study individual components. But most interesting and challenging is, what if you only have the output image? You don't know the camera, and you don't even have access to that camera. And what can we do? So what we do is through a good modeling. So we first need to understand what is the processing and what are the possibilities of those components. And if there are finite possibilities, we can cast it into a classification problem. If there's more continuous parameters, we can cast it as a parameter estimation. And it's also depending on the type of processing. Let me use color processing inside the digital camera as an illustrating example. If you have a 4 megapixel camera, and it produces a color picture, 4 megapixel, and each pixel is RGB numbers. But in fact, so you have this 4 meg times 3 numbers to play with. And actually inside your camera, the vast majority of today's camera has only one full resolution 4 meg sensor. And the color are sensed in an interleaved fashion, following an array, what we call as a color filter array, CFA. So basically for the red colors, the camera only directly sends every 4 pixel locations. The remaining ones are made up through exploring the relations through a process called color demosaiking, which is basically an interpolation process. The way the color is made up on each of the channel has really high impact on how good the picture would look like eventually. And it is one area all the manufacturers have heavy computation, they may have their proprietary technology, they have a competing. So from the forensic perspective, this is really nice, because if there is something unique to each vendor and each model, if we can analyze the relations between how the color is made up, those color interpolation algorithm and parameter, then we can use this as a good features and feeding into our decision logics. But in reality, the simple color interpolations, such as bilinear and bicubic, they are very simple to analyze. They are linear time environment systems, but they don't work well. They work well on this very smooth area, but when you have textures and edges, they tend to blur. So the state-of-art interpolation will try to explore some adaptations. The adaptations are, of course, along the edges and also the texture area. So the overall system is highly invariant and nonlinear. And what we did was we tried to cast this to account for some of those adaptations, but also make this estimation more more feasible, where we did some approximation. We classified the pixels in your picture into three major type of areas. Those smooth areas, those with dominating horizontal transitions and dominating vertical gradient. And then within each of the area and each of the channel, we approximate this interpolation as a linear time invariant filter, where such a kind of a region-based, type-based approximation, allowing us for each of type and the color channel, writing out a set of linear equations, where the x here is describing the color interpolation. Those are the coefficients we want to figure out. And we are looking at a finite support. And the b here are those interpolating ones we observe from the output. And a here, each row, are the pixels that we infer as a direct sense from your camera. And that's according to the color filter array pattern. So we can start with the candidate pattern, putting out this linear equation array, and then we can use least square type of robust estimation to estimate the coefficient. The coefficient set that is minimizing the overall fitting error will be giving us the estimate on the pattern as well as in the interpolation methods, interpolation coefficient set. And altogether, this is a joint estimation. And once we obtain that, and indeed we see across the different camera models, there is a major variations on how the car is made up. For smooth area, almost all the cameras has very similar ways because you don't really see much variation. But on the edge area, on the texture area, you need to see a good amount of variation. And then we can use those estimated interpolation to build classifiers. And what we did here was we don't even have the cameras. We just need to collect pictures from our students, faculty, friends, and family members. And we gathered about 20 cameras, and they are across 9 major camera brands. And you can see actually this data was collected a few years back. Canon was by far the most popular. We have 6 models coming from Canon, and a few from Nikon, and so on. And what we did is we use half our data for training. So we use that joint estimation to derive the color interpolation. We look at what are the representative color interpolation for each of the brand and the model. And then we feed into our testing data to see how well we can classify a given picture, which is the likely brand. And we have about 90% of the accuracy for 9 brands. And this is all the pictures has any content. We don't have any control. So we do not have control on what content. This can be sky, this can be your ski resort, can be our indoor and outdoor. So that requires our estimation to be resilient, to be more invariant to the content. And also you can have all the built-in compression. JPEG compression is one of the widely, and that can impose some of the noise perturbations in your data collected. But the least square formulations and algorithms are helping us to be more resilient. So they're helping us to be more less dependent on the input stream and tolerating compression and noise and emission noise. And this is just the 90% was just by yes.
I'm sorry. 90% means that if you look at a picture, the probability 90% it will be identified among these 19.
Yes. Okay. This is actually a data.
What do you think these concepts are? The 90% represents what?
So if we, actually this is a detailed result, it's called a confusion matrix, where if you have a testing tandem picture, we have 96% of the accuracy. And all the other, we have a star, which basically adding up as less than 4%. And we do this for every. And this diagonal line is giving us the overall accuracy. So we have about 90% for NAMA, just based on the color alone. If we adding on additional trace of evidence, such as noise, and also the way color is balanced, we actually can boost in that accuracy. So this is they are mentioned, in addition to color, there are also other uniqueness associated with this information processing image system. And for example, the noise. The reason initially motivating us to look at the noise is when we are dealing with a camera image, we have this nice interpolation, color filter array and interpolation. But scanned image does not have that structure. However, scanning image, what we did was very interesting. If you scan pictures and you do a wavelength analysis, and then you try to look at the histogram of some of the high band coefficient, it gives a really nice photographic picture. You see this really sharp Laplacian distribution. If the scanner is a little bit noisy but relatively on the high end, you see a little bit deviation from Laplacian but not too much. In the cheaper models, you will actually see a very nice fitting over the Gaussian. So through those statistical features, we actually can characterize some of the uniqueness of the imaging process. Maybe the sensor is cheaper and it has a low signal to noise ratio. So through this angle, we actually take a closer look at the noise properties. And we have this and other through prediction and through denoising to estimate the noise characteristics. And then combining them using the color and this noise attribute, we use those as features, and we can build a forensic analyzer. In the first round, we will look at those features, and we'll be able to tell you with a high confidence. We have a 94% accuracy tell you whether it is most likely from a standalone camera, which is really clean, higher quality, have that CFA interpolation, or a scanner version, which does not have that structure, but the noise is actually very profound. Or a cell phone camera, which is relatively noisy versions of the camera. Or it's a computer generated that does not imprint with that unique imaging traces. And then within each of the category, we can further utilize either the color or noise to help you identify which is an likely blend of the model. And that can be really a good tools for law enforcement and other agencies. And further, by exploring those traces, if this is a picture you know should be coming from a camera, you are expecting to see those color interpolation relations. If those traces are disappearing, or there's new additional traces adding them in, and that is a strong indication. Since the picture coming out from the camera, there's something else being done. So for example, if you see the inconsistency, the top ones in terms of color handling are most likely, the white is most likely from a Canon, and the bottom ones are most likely from a Sony, which indicated by black, and the gray are mostly in those smooth area where there's no much distinction across different cameras. By looking at this forensic map, you actually have a strong evidence. The picture is a merged version of two original sources. Its trustworthiness has to be serious questioned. Now, if the operation is more global, what we would see then is we can actually cast this under what we call as blind deconvolution, an iterative process to estimate what will be this module. We do a linear shifting variant approximation and to see what kind of unique pattern are there. And this, if you have smoothened a picture, since it's coming out from the camera, you will see a unique pattern, and it's a deviate from a wide spectrum, which is basically identity transformation. So far we have seen the intrinsic and embedded, and for the content fingerprinting, I would be really happy to talk to about more offline about this, where the Google also play a role, and you will see how we design the compact fingerprinting. More importantly, many of the industry players are interested in this, so they have ad hoc design, but we don't really know how good the overall performance is. Every time this is evaluated, you run through a benchmark, and then this company A is better than company B, but we don't really know better what techniques has good performance and has good adaptations toward what content. And our group actually have making an effort to do some analytical modeling to understand what techniques, what class of technique work best, and actually can combine with detection theory, and also some of the techniques that we learned from statistical physics can also be very helpful to us modeling this. So with invite you to visit our Google webpage and to learn some of our research on fingerprinting and others. Thank you very much for your attention.
Any questions or comments? Yes, sir.
Astronomers have a bunch of very old photographs. Astronomers have a bunch of very old photographs that they took back pre-modern digital cameras and flat plate images. Would your technique allow them to actually figure out what the essentially what the system function is of the camera and remove that so they can digitize them significantly or improve their imaging? There's sort of been debating whether or not it's worthwhile to do that. It looks like you can really improve what
I think potentially we could, but here, because the camera, the image, if it's originally an analog version, we first will have the digitization. We are dealing with a chain of processing, so, and don't have the, okay, let me go back with this. So we're dealing with a chain of processing. If this has a digitization, when we do the forensic inference, the first module, immediate to what we observe, is the best to analyze. But how deep we can go through this chain depends on the nature of the processing. So it may be more challenging, but if we have understand, say, these digitization devices, we can calibrate our analysis according to that. So I think potentially we can, and I would be interested to look at more.
This part here, the lens, that's the part that a lot of people are interested in. If you have the lens within, you know, the f-stop and the conjugate, the magnification used, this hopefully will allow you to very accurately measure the transfer function of the lens. What can you do with that in terms of improving the quality of the picture, reverse engineering, or telling the difference what camera made the picture?
Okay, that's actually a good question. Let me bring back to one of the slides that I really very quickly scanned through. What we can do about forensics depending on what's available to us. Right now, our focus is mainly on this completely non-intrusive, where we focus on those operations that are less dependent on the input. Interpolation is one good thing because all the input and output are carried in the picture we can observe. For other more multiplicative and other operations where both input and output is and the response function is unknown, and that will be under determined system. So for that, if we have control of the input or have an assumption on input, we call it a semi-non-intrusive. And what you see here is in our lab, we actually did some research on that for the color, the white balancing, which is a more multiplicative operations. And there, what we did is to design a good input, and we captured it, and helping us to use this knowledge about input and observed output to figure out the module we want to analyze. So my feeling is this would be more belonging to this if we have that information, but we have not yet looking into the evidence characteristic.
Well, maybe we can postpone the other questions to the break. Thank you very much.